A few of you have emailed me about your preferred grade ratios. So if you haven't done that yet, please let me know. You just got to give me 3 percentages for homework, quizzes, and the tests. So do that soon if you can. All right.
When is that due again?
I actually don't remember. It's on the syllabus, which I didn't bring with me today. But I'm not going to screw you if you forget to do it or something. I'll send out a reminder about it. All right. Excellent. Let's continue then. So we were doing proofs by induction about the language accepted by a DFA. I just wanted to do a couple more examples of that, and then we'll go on to something else. So these proofs can become a little bit more complicated if you, and it is sometimes necessary, sometimes you need to prove a lemma. So let's just try one more example. Well, I said 2 more examples where it involves stating and proving a lemma. Sometimes the hard part is like deciding exactly when such a lemma is necessary. This is a complicated looking DFA. Oops, no arrow there. Yes, arrow there. Okay, this is a DFA. So, there are several homework questions like this, although this one is a little more complicated than the ones that are on the homework because this is a new thing that I want to talk about. Your job is to decide what kinds of strings are accepted and then prove it. So first of all, we should write down some kind of formula. This accepts strings like, can anybody look, I know this one is a little complicated, but anyone feel like you can say some kind of formula, a to the n b or something like that, although it's not that for this one, but any ideas? You should be thinking about, like, what does it take to get here? Yeah?
Is it not b a to the n b?
B a to the n b. I like this. I have one. This is not quite right. For anybody feel like making a slight modification here? What I don't like about this is typically n is any natural number including 0. And actually, if the n is 0 here, then it's not accepted. You want to modify your description a little bit?
Where n is greater than 0.
Okay, you could say that in words, although doing words like that is going to make the proof slightly more cumbersome. I would rather write this as a formula like this. I would suggest you could either say b a to the n plus 1b, because that's another way of making it so that 0 doesn't count. You could put n plus 1 here, or to me, I would rather write it just like this. ba to the nb. Here, you could also say ba to the n plus 1b. Probably doesn't matter, but just the way I wrote it on my paper was like this. ba. And to me, when I look at the picture, this way of writing it seems more directly related to the picture. I see B and then A and then some more A's and then a B. So this is what is accepted. BA, A to the NB. All right, now we shall prove that. And this is one of those ones where you have to prove by induction using a lemma. And really the issue is kind of that this N is sort of in the middle of the string here. And the induction will not work. The traditional induction will not work because if I say if you think of this as a k and change it to a k plus 1, you don't actually see this whole thing as a substring. Anyway, what I'm going to do is state and prove this lemma. The reason the lemma is necessary is because the n is, I will say, isn't on the end. If the n were like the first letter, if the n were all the way on the left or all the way on the right, then this lemma would not be necessary. But what am I going to prove in the lemma? It should be something about what happens if I start in the starting state I'll call it S. I should give names to these states. I'll call the starting state S. I'll call this one T, U, and V. I probably don't need a name for the other one since we're never going to actually go there in accepting a string. But anyway, what I'm going to show is delta star of S and B a to the N is U. All right? I am cutting off the last letter because the induction, this is necessary in order to make the induction work the way you want it to. All right? You could also cut off the first two letters and do them separately. Either way would work. I'm just going to do it this way. All right? Anyway, this we do by induction, and this induction proof goes exactly like the ones last time. Would you mind if I kind of abbreviate this a little bit? This is, I will just say, by induction, as before, right? The base case, you use n equals 0, and then the whole thing, when n is 0, all of this says just delta star of S and BA equals U. And that is true because if I start in S and I go BA, I get to U. All right? And then the induction case is a little bit more complicated, but it goes very much like the ones that we did last time. And then that's the proof of the lemma. And then the actual statement that I want, I'll write this as the theorem. Can anyone say in formal terms, what is the actual complete thing that I'm trying to show here? It has to do with, delta star of something, something, something equals something. Any thoughts? Yeah?
Delta star of U, comma B equals V.
This is not what I was going to say, although that is like the last step to get from U to V, I think is what he's referring to. But I want to say this should be the full statement about what kinds of strings are accepted. I want to say, yeah?
Delta star S, comma B, A to the N, B equals V.
Yes, right. So this is meant to be the full statement about all of those are the accepted strings. What he said before is like one of the steps I'm going to use to justify this big thing here. All right. And then can we prove this? This proof does not require induction. It's just using the lemma. We should be able to prove that. Anybody see how to connect the dots here? Using the lemma? I think we can just start writing the proof. If I start in S and then I do all of this stuff, I already know that if I start in S and do this much, I get to U. So you want to do something about, you break this, this whole big string up into two parts. Could it be you need your memory to be refreshed over the weekend? Weren't you doing these proofs all weekend long? All night long? Maybe not. I must admit I wasn't myself. I'm going to break this into the two parts of this string. And remember the rule for this? It looks like delta star of delta star S BA A to the N. Sorry, I wrote N to the N. Don't make it no sense. B A to the N, comma B. Right? I'm sorry, I'm writing this in a bogus way. Sorry, I'm kind of like, my mind is wandering here. I have a calculus class at 9:30, and then right after that, they all came to my office and were doing calculus problems until right before I came here, so I'm like, my mind is messed up. I really should have, this is not wrong what I wrote, but really I meant to write just like what we're starting with, right, to make this into a reasonable looking proof. You should start with this, right? That is equal to that. Sorry for moving stuff around. Right? I'm starting with this thing. It equals this. That's that product about delta star, that weird property, weird looking property about starting from here and then going on from there. And then the first thing that you see in here, delta star of S, B, A to the N, that I use the lemma and it equals U. So this is delta star of U, comma B, right? This is by the lemma, if you like. And then what is delta star of u comma b? You just look at the diagram. This means if I'm in state u and I do b, what does it look like? And it is v. So this equals v. And that is what we wanted to show. Right? We were supposed to show this thing equals v. All right. I don't know if you like writing proofs. These proofs, you don't have to have like some kind of big idea. It's just mostly you can let the formalism play itself out. It's just a matter of being able to plug stuff in properly. All right. Great. I got one more, and then I have one for you all to try of this type. My one more is yet another example where these can be a little trickier. So sometimes our formula, all the examples we've done so far have been things with like exponents of n, right? A, b to the n, a, something like that. Sometimes our formula has, let's say, something like, x's in it. Like, I'm thinking of something like ax, such that x is in sigma star. This would mean all strings starting with a, right? But it's not something that you can write using exponents because we don't actually know what else. This is all strings starting with a. But then after the a could be anything, not just like powers of b or something like that. So this is a very common kind of a language that you would want to discuss. And so we need to talk about how you would deal with such a thing. It's less clear how you're supposed to use induction on that because I don't see n, right? You always have to have some variable that you do the induction with. So let's try one example like this. It's not such a big deal. Let me just say for these, we do induction on the length of x, which I'll call n. This is the length of x. All right? Remember, that's how we write the length of a string is with those sort of absolute value signs. So even though you don't see a variable n in there, you can always make the arguments work by doing induction on the length of x. And you can call that n. You can call it whatever you want, but that's where we do the induction. All right, let's just try a simple one like that. Actually, this is exactly that language. This is a DFA which accepts any string that starts with A, and it rejects a string that starts with B. All right, so here this accepts the set AX, where X is any string. All right, and I would like to prove that. So formally speaking, the first step is always to write down sort of formally what exactly is it that we are saying that it accepts AX. Well, in terms of symbols, I should give names to the states, at least the states that I care about, which are S and T. That other state, we're never going to go there, so we don't really have to give a name to it. But formally speaking, can anybody describe in formal terms what does it look like if I want to say that AX is accepted here? It's going to involve deltas. I give you a hint. Delta star something 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 equals something. I want to say AX is accepted. Yeah?
Delta star S comma AX
Yeah. Equals T. Yeah, that's the accepting state. Great. This is what I want to show. All right. And we have to do this by induction on the length of S. So maybe I'll write this as my theorem, right, which I want to show, and I'm going to prove this by induction. delta star of S AX equals T. I hope, nobody was saying this. I hope that this makes sense to everybody. I mean, this is like, you can't even get anywhere if you don't know where to start with your statement like this. But I hope everybody knows I'm saying this is the formal way of saying that AX is accepted. It means if I start in state S and then I do AX, I end up in the accepting state, which is T. All right. So that's the theorem that I want to show. I will write something like this. Let n equal the length of x, and then we'll do induction on n. Right? There's no n directly written in the formula, but it's okay. You have to make up your own n. And you better do it n as the length of x. All right, we'll do induction on n. Okay, let's do it. The base case shall be n equals 0, as usual. I want to show delta star of S AX equals T when the length of x equals 0. What can you say? When the length of x is 0, that means x is the empty string. And if x is the empty string, I'll say something like, since the length of x is 0, that means x equals the empty string. So delta star of S and AX is equal to delta star of S and A. And what is delta star of S and A? Just means if you're in state S and you see A, you get T. And this is what we wanted to show. Delta star of S and AX is equal to T. All right? So as usual, the base case is usually, going to be easy, right? The base case is always when x is the empty string. Okay? And then the induction step. Let's try. All right. So for this one, we begin by writing the induction hypothesis. I say we assume. So here you have to say a few kind of words here. I'm going to assume that this equals T when the length of x is K. And then what we have to show is that that equals T when the length of x is K plus 1. All right? So we'll show same thing. When length of x equals K plus 1. Right? This proof, I would say, on its surface maybe looks slightly more confusing because actually, like on the surface, these two equations are exactly the same. They're written exactly the same. It's just we assume that that this is true when the length of x is k, and we have to also show that this is still true when the length of x is k plus 1. I don't know if that's confusing. It's not so bad though. All right. How do we actually do the proof? So I'm going to say, let the length of x be k plus 1. And here's sort of the key step. These proofs are, I guess, a little bit, you have to write a little bit more stuff here. But if the length of x is k plus 1, that means x consists of k letters followed by one more letter, right? Or you could write it the other way around. One letter at the beginning followed by k more letters. I'm going to write it whatever, the way I said the first time. So if the length of x is k plus 1, so maybe I will write it this way. X equals YL. That's a L right there. I write my L's with a loopy thing there so that it doesn't look like the number 1. But anyway, I'm going to write x equals YL where the length of y is k and L is a single letter. All right? This is what allows us to use the induction hypothesis, is that y now has length k, and so we can use the induction hypothesis on y. All right? So let x be k plus 1 length. That means I can write x as something with a letter on the end, so that L is a single letter. And now we can finish the argument. So we have now delta star S AX, all right? X is YL, so I'm just going to plug in instead of x, AYL, where L is a single letter. And now I'm going to do my delta star thing by breaking up this string here, and I'm going to break it up in this way. AY followed by L. So now it says delta star S A Y comma L, like that. And what's the point of that? The point of that is here S A Y, Y has length K, and so I can use the induction hypothesis there. All right? This is true whenever the length of that string is K, and so it can be applied to this string right here, which has length K. And so here is my induction hypothesis, T, comma, L, right? This is the induction hypothesis step. And the reason this works is since the length of Y is K, right? That means we can use the induction hypothesis on that string. The induction hypothesis only applies when it's A followed by a string of length K, but that's what we have here. All right, and then to finish it off, what is delta star of T and some letter? Now, I don't know what letter this is, but on the diagram you can see that it doesn't matter. If I'm in state T and I do one single letter, it's just going to be T again, right? Whether it's a A or a B, it doesn't matter. So here, delta star of TL is T. And that's what I wanted to show, right? I wanted to show that delta star of S and AX is T. There you go. All right. This is how we do when you don't have an N. These are a little, I suppose, a little trickier than the other ones when you can see the N in the formula directly. Any questions about that? I have one for you all to try. Yeah? All right, let's try. This one is actually a little tricky. It is some kind of a combination of the two types. See how you do. I don't know if this is too hard. It's actually a simpler looking diagram, but I'll call them S and T. All right, your job is find which strings are accepted and then prove it. Maybe I'll say, just to make sure everybody gets started off on the right foot here, find which strings are accepted and then prove it. Can anybody say, first of all, like what are the strings that are accepted here? The language of the machine. Anybody think you can say like a formula? It could involve like exponents, or it could involve, you know, just any old string x, something like that. What do you say?
Did you say B to the N A?
B to the N A. This is good. I want to say one. I have something to add at the end there. Anyone feel like? B to the N A is certainly accepted. You go B's and then A, and it's accepted. Could you do stuff after the A? I think actually you could. You could do, in fact, anything you want after the A, and it would still be accepted, right? So the way I would write that is B to the N A X, where X can be any string, all right? So what's interesting about this one is actually we have sort of two separate ingredients which require induction. There's one here, the N, and then there's one here, the X, right? Both require inductions. I don't know if you ever did you ever do a double induction in your discrete math class? This is like only for the professionals do we do double induction. You can actually do sort of two inductions at once, although it's not really necessary here. I would do this, I would split this out using a lemma. So I'm not going to do these proofs, I'll leave this up to you, but anyone want to suggest a lemma that handles the first induction, like the power of B there, and then another lemma, or then, you know, this is, I'm going to say, to handle the N. I would do something like, just to start, delta star of B to the N, comma, sorry, I got in the wrong order, S, B to the N is S, right? That's what I would prove first. This handles the N part at least. So prove that, and then you can prove the theorem, which would say delta star of S and b to the n ax equals t. So this one is, the first one will be induction on this n, and the second will be induction using the length of x. All right? See what you think. I'm going to walk around and see how you're doing. I hope that this is coming together for everybody. It's a little tricky. Then we're going on to something completely different. So you're doing this part first. Yep. And that should be induction using n. So you should start with like a base case for the n here. You should do the base case for the lemma. Yeah, the lemma has to use induction on n. So each of those two parts is a different induction, so you should have a base case first and then the inductive case. Yeah, looks good so far. Yeah. And then we can move from there. Oh, you should actually probably, before you write that, you should write this induction. It's with the K. Alright. You did the lemma? Just limit up by that line. I think you should split it up. No, you can read like another line.
Okay, so, yeah.
Yeah, you can just do this directly back there. Prediction on that text. Maybe it's not so good, because I use L as a single number.
Oh, okay.
Using L as a number, sure.
Okay, so you do it like that, okay.
How's it going? Refreshing your memory. Yeah, when n is 0, 7 is just this S empty string. Yeah, start here and do nothing. This. Yeah. Yep. Yeah, so I would, you had to write something out and say, probably delta looks like S. Delta, I would say delta star of S comma b to the 0 is the same as S comma Congratulations, Lana. I skipped it before, but I needed it. How's it going? Okay. Great.
I guess that might be true.
Are you doing the base case still? Or?
Yeah, I was just looking at
So, yeah, for the base case, it means you can put 0 there.
yeah, I think that's. I just mentioned that. I just said this.
Oh, okay, yeah. Yeah, then it's this.
Okay. Alright.
And here, this is pretty good. This way. I think you're thinking of this,
Yeah.
but in this case, it's just M. You can just K there.
H may get K. Okay.
Yeah, I mean, here you're saying N.
Yeah.
Still all right here? How's it going? Got your dilemma? Alright, so this is where you're putting the you're gonna prove that this equals 2. Wait, what we're proving? Okay. You'll see, I'm gonna write it so that's a good structure. Yeah, I think you're good. So this is the proof of the lemma. Excellent. All good here? Mm-hmm. You got this. Mhm. So there should be yeah, I think it's actually not. Where do you use the induction process? So, yeah, but see, that's not actually what the induction process is. You really don't want to use something like this. Because the induction process is about let's start this. So not just a something, but if you left the beginning in there, then. Okay. How's it going? Just working on the lemma? Yeah, good so far. Doing okay? Started over. How's it going here? Still good in there? Mhm. Yeah, so you have to put,
you really have to write AX and then separate it up where the length x equals k. Because AK doesn't really make sense. If k is a number, then you can't really say A times k. Yeah, right. And you want to show, put x here again, and then square.
And then where do we go?
Yeah, then you should. Something like that. You write x. If x has length k plus 1, then that means it has a length k part and then one more letter. That's the idea.
Maybe we should talk about these. I said I had more stuff to do, but I don't know if we're going to get, if we have enough time. So let's just go over this. This, in my opinion, is kind of a tricky one. The lemma, I would say, is not especially tricky. I'm not going to say it's easy, but it's like the ones we did last time. I wrote out the base case here, the induction case. As I was walking around, pretty much everybody did the lemma great, so I'm going to breeze through this. We assume delta star of s and b to the k is s, and then I want to show delta star of s and b to the k plus 1 is s, right? I'm going to move this down. Okay, how to show that? We have delta star s b to the k plus 1. I'm going to split that up as delta star s and b to the k, comma, one more b, right? I hope that's what you said. And then that first s and b to the k, I use induction hypothesis. And this looks like delta star of s, comma, b. So the induction hypothesis said delta star of s, comma, b to the k is s. So that's right here. And then delta star of s and b means if I'm in state s and I do b, where do I go? And the answer is s. So this is s. As desired. That's another thing sometimes people write at the end of proofs. I actually write that in, if you ever read my research articles, which I don't necessarily suggest, but they say as desired a lot at the end of the proofs. I don't say shewn in public in front of other researchers. All right, great. That's only in the DMs, you know what I'm saying? That was the lemma. Okay, what about the theorem as a whole? So I'm going to use that lemma as part of the proof of the real thing that I'm interested in is this theorem here. And this is the one with the sort of induction on the length. So I'm going to say this is a proof by induction on the length of x. And the length of x, maybe I'll call, well, it doesn't really matter what you call it. I don't really want to call this n because I already see an n right there. N already means something else. But anyway, I'm going to do the base case. This is when the length of x is 0. I want to show delta star of s, comma, b to the n ax equals t when the length of x equals 0. But when the length of x is 0, that means x is the empty string. And then this is going to be easy to show. So I will say something like, if the length x equals 0, then x is the empty string. So we get delta star s b to the n a x is the same as delta star s b to the n a, like empty string, right? And then this, how did you handle this? And I know some people made it this far. I need to show that this equals t. Anybody get to a similar spot as this? When I did this, I used the lemma to prove this step. Anybody agree? Nobody wants to say it, or nobody knows it? I can't tell. Yeah?
Right, that's a composition of s, b to the n, a.
Yeah. Break up b to the n a as b to the n followed by a. So this is going to be delta star of s, b to the n, comma a. Yeah, great. Somebody knows. Maybe, I hope you all know. I can't tell. I've been doing volumes of revolution all morning. All right? And then S comma B to the n, that's the lemma, right? Delta star, that's S, according to the lemma. This is by the lemma. This is where I use the lemma. And then what is delta star of S and A? That's T, by looking at the diagram, right? The arrow from S with an A on it is T. As desired. This is the base case. This is like the longest base case we've ever done. Sometimes the base case does require, I mean, I wouldn't say it's a hard argument or anything, but sometimes the base case does require some, at least small amount of work. Okay, and the induction case. The induction case is, we assume, my induction hypothesis would be that delta star of S and B to the n ax equals T when the length of x is k, and I want to show the same thing when the length of x is k plus 1. All right? And the way that I'm pretty much always going to write these up is I say let the length of x be k plus 1. Then we can write x as something like y times L, where L is one more letter. All right? Where y, the length of y is k, and L is a letter. A single letter. All right. And then we can write down our thing that we want to show. Then the point is we can use the induction hypothesis on y, but not on x. So now what is what I want to show? I start with what I want to show. Delta star of S, B to the n ax, and try to simplify here. First I'm going to plug in x equals yl. If you know what you're doing, each step kind of follows naturally from the previous one, although it is a bit, there's a lot going on here. So the first time you do this, it seems a little crazy maybe. All right, S, B to the n, A, Y, L. And now I'm going to split this up. B to the n, because I intend to use the induction hypothesis, which looks like this. B to the n, A, something. So I'm going to split this up as the little, this thing first, followed by L, right? So this is delta star, S, B to the n, A, Y, comma, L. And then that first part, I can use the induction hypothesis because the length of y is k. So this is my induction hypothesis step, delta star outside, T, comma, L. And then according to the diagram, if I'm in state T and I do one more letter, it doesn't matter what that letter is, the answer is still going to be in state T. So this is T, which is what we needed to prove. All right? Any thoughts about that? These are complicated, and it'll take you, several minutes to write down the whole proof. Even if you know exactly what you're doing, these are not entirely straightforward all the time. All right. I think maybe that'll do. We have a few more minutes, but I wanted to go on to something completely different. I don't know if anybody's getting worried at this point. Actually, this kind of thing is not what this whole class is going to be about, so I don't know if you were getting worried. We will every so often write sort of proofs like this with lots of abstract-looking symbols, although I would say that there's not a lot of abstract ideas. It's just a matter of sort of expressing fairly ordinary ideas in this abstract formal symbols. But yeah, anyway, next time we're going to talk about something completely different. Still about DFAs. But. All right, let me know if you got homework questions. I'd be happy to chat about it. You will see problems that are basically like easier versions of what we were doing today. All right.